Am I on? Can you guys hear me and see me? Zoom was acting kind of funny here today. Where is everybody today? Not so many participants. I would have thought today would be the day everybody shows up. All right, well, let's get started. First of all, do you have any questions for me? Anything that you need to ask? One thing I do want to draw to your attention, hang on a second, let me find this. I want to share my screen with you. There it is. We were talking last time about this guy Conway, a mathematician who just passed away, and I checked later in the day for one of the web comics that I check frequently. It comes out 3 times a week, and it's called XKCD, which, as far as I know, doesn't stand for anything. But they had a little tribute. Let's see, let me do this to here. You guys getting that? So this is the XKCD cartoon from, it's actually from Monday, and they are actually showing an instance of the Conway game of life, and it starts off in generation 0. It's just a little picture of like a stick person. But then when you go through the rules of how the generations are computed, you can see that it includes this little glider, it's what it's called, that goes off on the diagonal, and it keeps recreating its same shape, but in different positions. It goes on endlessly. I suppose this is supposed to be thinking about his spirit flying off to the heavens or something. But anyway, it was a cute homage to John Conway and his Conway's game of life. So there's that. Next is the exam. So we were talking about this last time. The topics will be the ones that I think we discussed last time. Basically, all the sections that we've covered since the last exam, and they are all in chapters 4, 6, and 7. We did spend a little time, at least one day, talking about that RSA encryption algorithm, mostly as a way of illustrating the Fermat-Little theorem and Euler's theorem. So I'd like you guys to be familiar with those. That's just the chapters we've done from, the sections we've done from those chapters. It's your last chance to ask. Is there anything about those topics that you need me to clarify? Well, you guys are really quiet today. Usually I hear some rustling or somebody's got a question or something. Can you at least hear me?
We can hear you.
Okay, thanks. All right, so setting the exam aside, I would like to start a new chapter that's not going to be on the exam, although it will build from some of the same topics. So this is going to be now in chapter 9, and this is a topic called primitive roots. So let me write some things down for you so you can see. Oopsie. Never seem to get this oriented properly. Fine. So the term is primitive roots. I don't really know where that terminology comes from, but here's the deal. I want to do this primarily for a prime modulus, but let's assume that P is a prime. Then one of the things we know, I mean, Fermat's little theorem tells us something about the order of any element modulo P. And by that, I mean, if you take any integer x that's one of the congruence classes mod P other than 0, So you may remember this little x means we're looking at an invertible congruence class. That's the times symbol. This is the letter x, and that's the times symbol. The conclusion is that x to the p minus 1 power is congruent to 1 modulo p. Now, although this is true, this is not the only exponent on x that will give us a 1. We've been able to take advantage of the fact that multiples of p minus 1 will also serve the same role. We've used that, well, for example, when we did that exercise one day with the RSA algorithm, it was to our advantage to know that there were higher exponents, multiples of p minus 1 that would work as well. However, obviously there will be, at least for some x's, there will be lower exponents that can also work. I mean, it's obvious that if you take just 1 to any power, that's always going to be congruent to 1 modulo p. So using an exponent of p minus 1 is not, it's not the lowest that you can get away with. Of course, 1 is the only number that you can raise to an arbitrary exponent and get a 1. You also had some homework exercises that talked about situations where an exponent of 2 could be used. There are numbers where x squared will be congruent to 1 modulo p, but in the case where the modulus is prime, what I asked you to think about in the homework is there's not too many of them. In fact, we've discussed exactly this situation before. If you write out this by saying that x squared minus 1 is a multiple of p, then you're saying that p divides the product of x minus 1 and x plus 1. And if p is a prime, then you know that that implies that either p divides x minus 1 or p divides x plus 1. So here's the two conclusions that you get to discover that there are only the two possible square roots of 1 in Z mod p. But at least there are some, and so you see that there are lower exponents that you can use on some x's. And so when you start playing around with some of these examples, there's a few questions that do start to arise in a natural way, and when you ask them, you discover that, hey, actually asking these questions turns out to be useful. So let me make the following definition. If you do take an invertible congruence class, mod p, p is going to be prime all day, then we define this set of symbols. ORD stands for order, and it's the order of x mod p. So I'll put a little p in there as a subscript somewhere. This, I'll just, for brevity, let me just give this a name n. That this quantity means it's the smallest positive integer n for which this kind of a congruence will be equal to 1. It's the least positive integer for which, x to the n is congruent to 1 modulo p. So if you want to go back to like the beginning of the semester when we were just trying to get used to exactly what makes the integers be, or the natural numbers be what they are, one of our properties was that any non-empty set of natural numbers has a smallest element. I can use that idea to sort of re-describe what this order thing is. It is, you can think of it as the minimum of this collection of natural numbers, such that, well, first of all, I don't want you to use 0, but apart from 0, I want it to be true that x to the n is congruent to 1 modulo p. And in order for us to use the well-ordering principle to define this as the minimum, well, every non-empty set of natural numbers has a minimum, so I have to know why this set is non-empty. How do I know there's any non-zero natural number which I can use on this exponent to get a 1? And the answer is that this Fermat's theorem guarantees for us that there is one. In fact, you don't have to wait too long. You don't have to go up too high to find such an exponent. Of course, this does assume that you start off with an invertible element modulo p. You have to start off with an x that's not divisible by p. So that theorem of Fermat guarantees that this is not empty. It's not the empty set, assuming that p does not divide x. If, on the other hand, p does divide x, you're in trouble, because that means that x is congruent to 0 mod p, and all of its powers will be congruent to 0 mod p. So this really would be the empty set, and so the minimum is not defined. That's got to be, that's the case for this thing called the order as well. I'm only defining it for invertible congruence classes mod p. For if x is a multiple of p, then this is not even defined. It kind of goes without saying, since I'm doing all of my calculations modulo p, then you can think about this element of z mod p cross as actually literally being a congruence class of integers, or you can think of it as being an actual integer, but then the order of p mod x would be the same as the order of p modulo x prime whenever x and x prime are congruent to each other modulo p. So I will sort of gloss over the difference between the integers and the integers mod p. Obviously, there's infinitely many integers, and there's only p elements in here, well, p minus 1 elements in here. So when I write down a symbol that looks like I'm talking about an integer, you know I'm actually talking about the congruence class of that integer modulo p. All right, let's try some examples, shall we? So let's take a prime that's not too big so I can actually work these things out. The elements of z mod p cross are 1, 2, 3, 4, 5, and 6. I mean, the congruence classes of them modulo 7. When you look at the orders of these classes, mod 7, they're pretty easy. The order on 1 is just going to be 1. In fact, that's a little proposition that you should be able to prove off on the side. It says for all primes p, the order mod p of an invertible congruence class x is 1 if and only if that number x is 1, or it's congruent to 1 modulo p. So yes, 1 to the first power is already congruent to 1 precisely when x is congruent to 1. So I'm going to get the order equal to 1 in this case and not in any of the others. 6 is also an easy one to get the order of, because 6 is the same as negative 1. And we've already discussed the fact that negative 1 is another square root of 1. So when you take 6 and square it, that does bring you back to a 1. And this result that I had here, this talked about finding exactly the elements for which the order of the element was 2. I'll add that to this proposition here. The order of p, the order of x mod p is the number 2, precisely when x is congruent to negative 1 mod p. And yes, you do have to be careful when p is the prime 2, then a number x is congruent to 1 if and only if it's congruent to negative 1, in which case it sounds like I'm saying things that are contradictory here, so let me rule that possibility out. I don't want you to use the prime 2 in that case. This would have been a very short example if I had chosen the prime 2 in the first place. For the prime 2, there's only one congruence class, and the order of that congruence class is a 1. All right, so I've got the orders of a couple of these elements. Now, the rest of these take just a little bit more work. The number 2, well, when you raise it to the first power, you didn't get a 1. When you square it, you still didn't get a 1. But when you cube it, 2 cubed is 8, which is congruent to 1, mod 7. So the smallest positive exponent that worked was a 3. Let me skip over this one now to the number 4. Since 4 is the square of 2, I kind of already know what's going to happen. 4, I mean, it's listed among, the powers of 4 will be listed among the powers of 2, and I've already found out a power of 2 that'll take me back to 1. So you'll see here, watch. If I take 4 to the first power, that's the same as 2 squared. That wasn't 1. 4 to the second power is the same as 2 to the fourth. Well, the first 3 powers of 2 came back to being congruent to 1 already. So 2 to the fourth, 4 squared is the same as 2 to the fourth. And that'll just be congruent to 2 to the first power, which is not 1. But 4 cubed is 64, which is 1 more than a multiple of 7. So 4 cubed is back to 1 modulo 7. So the order of 4 is also a 3. Now what's left are 3 and 5, and I'm going to have to do a little bit of arithmetic for you. Let's run through the powers of 3. 3 to the first is obviously 3. 3 squared is 9, which is congruent to 2. 3 cubed is congruent to 3 of those, which is 6. That's congruent to negative 1. So now 3 to the fourth means I multiply this one by by another 3. So I'll get the negative of what I had in the previous column. 3 to the fifth is congruent to 3 times those, so that'll be, the negative of those. And finally, 3 to the sixth is congruent to the negative of this, which is plus 1. So I got it, finally. I did get a power of 3 that gave me a 1, but it didn't happen until I went all the way to the exponent that Fermat's theorem told me I could count on as like a backup. I knew that any one of these numbers, when raised to the 6th power, would automatically give me a 1. And sure enough, for the number 3, I had to go all the way through the 6 powers of 3 until I got back to a 1. And I'll spare you the arithmetic, but by doing really just as many steps, you'll discover that, well, actually 5 cubed will be equal to negative 1. So those 3 numbers will be the negatives of those. It'll all work out the same. So the order of 5 mod 7 is 6. It takes a while to get used to putting those 3 numbers into one sentence and remembering which one plays which role, but you can do it. I have confidence in you. So the order of 5 mod 7 is 6, because 5 to the 6th power is 1 mod 7, but no lower power of 5 has that property. All right. Everybody with me? No questions. All right. Question, you good? No?
No question.
Okay, you made it.
Yes, make sure that we can hear you.
Yeah. When you, what I have noticed, guys, is that every time, if your mic is on, which is great, just keep in mind that the minute that you rustle a paper or something, then my screen will switch to your camera if you have it on, or your avatar, so I'll think that you're trying to reach me. Okay, now I want to start proving some theorems about this concept of order. So here's one that's it's important for us. For any prime p, and for any integer x that's prime to p, I can tell you one thing about this order. It was defined as the smallest positive integer exponent that would give you a 1. And the Fermat theorem says that at least the exponent of p minus 1 will work. So for sure, the order of p mod x will always be less than or equal to p minus 1. So I'll put that in for a second. But really, I want to say something stronger. I mean, this just comes from just making the observation of the Fermat theorem and the definition of order. But the stronger statement is that, in fact, the order will always be a divisor of p minus 1. So in the case that we just did, where the prime was 7, you'll notice that I never got anything of orders 4 or 5, just these numbers that are divisors of 6. All right, and the proof comes back to a theme that we've had a few times. In fact, I meant to remark to you guys that This uses an idea that we had all the way back on the previous exam. Do you remember I gave you this question? I don't remember exactly how it was phrased, but I said if n and m are co-prime integers and x is a real number and you knew that nx was an integer and also mx was an integer, then the conclusion was that x itself was an integer. And the proof that I gave you at the time just said, hey, we're going to use the Bezout theorem and I'll write down some magic stuff and that'll give you the conclusion. And when I wrote that, I warned you that we'll be doing using that similar trick in the future. Well, the future is now. So I've actually used the proof already on other occasions, but let me make a point of illustrating it. What we have are two numbers. This will be the n and this will be the m, and they have the feature that on the one hand, x to the n is congruent to 1 modulo p, and that's because of the definition of order. On the other hand, we know that x to the m is congruent to 1 modulo p, and that's true because of the Fermat theorem. And now I'm going to say, well, okay, what if you have statements about two integers that sort of give you some information about an x? Can you combine them to get more refined information? And the answer is yes, if you use the Bezout theorem. So now find integers u and v, but possibly negative, but find integers u and v with the feature that n times u plus m times v is equal to the GCD of these two things. And that's possible thanks to the Bezout lemma. Now what I want to do is to use this long expression in the same place that I used the n and the m. That was the same idea that I had here. I used this long expression exactly where the n and the m were. So if I do that in this case, what I'll discover is that x to this GCD power is the same as x to the nu plus mv, but by my laws of exponents, that's the same as x to the n to the u times x to the m to the v. Well, if you already know that x to the n is congruent to 1, and you know that x to the m is congruent to 1, then the whole mess of it is also congruent to 1. So that means that if you have identified what you think is the order of n of x mod p, then when you compute the GCD of that number with with this m, this p minus 1, then that will tell you that that GCD is now another exponent that you could use on x to get a 1. The problem with that is that n was defined to be the smallest positive exponent that would work in this case. So by the minimality, well, so let me put an extra line in here. You know that the GCD of m and n is, among other things, it's got to be less than or equal to n. It's supposed to be a divisor of n, should be less than or equal to n. So by the minimality of this thing that I defined as the order, you shouldn't be able to find something that's smaller than n that will still work as that exponent. I mean, the GCD is still a positive integer, and if it still works as an exponent to give you a 1, then something is wrong unless we discover that that means the GCD of n and m is actually n. So it wasn't any smaller. That exponent that you had was the same as the one that you had before. Of course, now on the other hand, what that means is that, oh, I was looking for a large common divisor of n and m, and I found out that the GCD turned out to be n. Well, sure, n divides n. Everybody recognizes that. But to tell me that n is the GCD of these two numbers means, in particular, that n divides m. And remember, m was this p minus 1 that I had in the first place. And that gives me the conclusion of the theorem that I wrote at the beginning. There's the n, and it divides the m. So these orders are reasonably small numbers. I mean, they're always less than or equal to p minus 1, but in fact, they're kind of limited. They only turn out to be the divisors of p minus 1. That's very handy if you have something like, oh, I don't know, what if p is equal to 23? In that case, p minus 1 factors only as 2 times 11, and therefore the orders of the elements mod p, mod 23, they can only be 1, 2, 11, or 22. Those are the only possible orders. And we've already decided when this happens, the only x for which the order is equal to 1 is x equals 1. And the only order for which x is equal to 2 would be x equals negative 1, congruent to negative 1. So all the other invertible congruence classes mod 23, let's keep track here. There's 22 invertible congruence classes. We've got 2 of them right here, so there's 20 more remaining. There's 20 congruence classes modulo 23, and they are all going to have either order 11 or order 22. Those are the only possible orders for an element modulo 23. Now, I can try. Yes, certainly, please do.
So, do we have an element whose order is all of these divisors? Like, do we have at least one element whose order turns out to be either of these divisors? So, do we have an order for each of the divisors of?
Yes, that's a good question. So when I first defined the definition of order, you discover at this point that the order of an element mod p is a number somewhere between 1 and p minus 1. But already this theorem has ruled out some of those as potential orders, right? You can't just have any number that's less than p minus 1. It actually has to be a divisor of p minus 1. And so now you might similarly ask, well, are there some further restrictions? Maybe some of these things don't occur. And that's an excellent question, and it turns out I have an answer, but let me warn you, I can do a lot of what I'm doing with a composite modulus as well, but I'm sticking with primes right now precisely because I have an affirmative answer to your question. For primes p, what turns out to be true is any of the divisors of p minus 1 actually is an order of some element or elements of Z mod P cross. That's a theorem, and it's not obvious by any means. It's not even easy to prove. But we'll work on it. And I'll use this P equals 23 as an example. But I'll tell you what, I'll write that in as a definition since you asked about it.
And we will have a connection with the sigma function and the maybe Mobius function and the primitive roots. From the previous chapter.
Yes, I'm not. Did you have a connection in mind to the sigma function?
Because it was related to the divisors.
Yes, but the sigma function and so on, those were looking at counting just how many divisors there were. And so here what I did is I listed the 4 possible divisors of 22. What turns out to be more important for us is not just counting adding in one extra finger every time I see those. In fact, what is a little more relevant in this case would be to do something like range over all of the divisors of p minus 1 and count how many congruence classes have this or this or this or this as their order. So I'm not really sure I have a good connection to what we had in the previous chapter just yet. Let me think about it if there's a different answer from the one I'm going to give you. But first, let me make the definition, and it's actually this word that I put in at the beginning of the hour. I can tell you what a primitive root is, at least. I mean, when it exists, you'll have a definition for it. So a primitive root, mod p, is an integer, well, or a congruence class of integers. It'll have to be an invertible congruence class mod p, with the feature that the order mod p of this integer is that maximal value. It's exactly p minus 1. And part of your question is, well, for every prime p, does there necessarily exist a primitive root? And that's a good question, and we'll try to answer that. I'm not quite ready for that. I want to do some other things first. What I'd like to do is to talk to you a little bit about how I know that the orders of some elements will be less than p minus 1. In other words, I can rule out some of the congruence classes mod p and assure you that they are not primitive roots. Oh, by the way, let's just go back to that one example we did, mod 7. These were the orders of for the different values of x, these are the orders of these elements modulo 7. So was there a primitive root in this case? The answer is yes, there were 2 of them. So one element had order 1, one element had order 2, and then we had 2 primitive roots and 2 other elements. So as I was saying here, if we did a sort of a count corresponding to this, there's one element of order 1, one element of order negative 1. We had, in that case, we had exactly 2 primitive roots, and then there were 2 others. And you can make a conjecture as to what you think might happen in this case as well. Well, you can either check it by kind of a laborious calculation, or we'll start to think about what we can determine about the structure of these things, these sets, the Z mod P cross. All right, so how about this? Here's a theorem. I'll start it this way. If, well, let's just start off slow here. If x is a primitive root mod p, then I can tell you the order mod p of x squared. The order of p mod x squared would be this number. Now, this is a divisor of p minus 1, like it's supposed to be. But it's the precise divisor of p minus 1 that turns out to be the order of this one. So let's see how you would check this. Let's just make sure that you understand how you're computing the order. What I need to know is, I need to know what the smallest positive exponent on this number is that'll get me back to 1. So, well, somebody seems to have proposed something that will work. Is it true that if I use this exponent on this base, that I get something that's congruent to 1 modulo p? Well, of course it is, because thanks to your laws of exponents, this is the same as x to the p minus 1. And thanks to the Fermat theorem, that's congruent to 1 mod p. So we've completed half of the battle here. We've decided at least that this is an exponent that can go on this base to give me a 1. But the question is it the smallest exponent that would work? So let's see, I'll do that as a proof by contradiction. Let's suppose that that's not true. If k is any other number that works in the sense that if you take the base x squared and raise it to the kth power, and that gives you a 1. Well, then what you've just discovered is that, again, the laws of exponents, x to the 2k power has just been made congruent to 1 modulo p. On the other hand, when you say at the beginning that x is a primitive root mod p, well, that means that the smallest exponent you're supposed to put on x that'll ever give you a 1 is p minus 1 itself. So if this is an exponent that you can put on the x to get a 1, that forces 2k to be at least that order. And if the order is known to be p minus 1, then that means I know something about k. K is now greater than or equal to p minus 1 over 2. So here I have identified an exponent that goes on the x squared to give me a 1. And now I'm thinking about all the exponents that I could possibly put on, and I discovered all the positive exponents, and I discovered that they are all at least that big. So therefore, the minimum the minimum exponent, the minimum k, is going to be precisely the p minus 1 over 2. Okay, that's what I wanted to prove. So when you look at certain squares, I know exactly what their order is. And in fact, in a very similar way, you discover that anytime you take any square, whether it's the square of a primitive root or anything else, then the order will be less than or equal to p minus 1 over 2. In other words, none of the squares is ever a primitive root. So let's have that as a theorem. If x is I'll say it this way. If x is any of the invertible elements mod p, then x squared is not a primitive root. And the reason this is actually an easy one, because I know that if I take x squared, it's the same starting line as I had in the previous proof. X squared raised to the p minus 1 power, that's just x to the p minus 1, and we know that that's already congruent to 1 modulo p by the Fermat theorem. So if a primitive root is one that you can never use a smaller exponent than p minus 1 to get something congruent to 1, well, I guess this guy's a loser, because I've already found a smaller exponent that works. Since this p minus 1 over 2 is obviously smaller than p minus 1, that means that x squared, well, it means that the order of x squared modulo p is at most p minus 1 over 2, which means it's less than p minus 1. So x squared is not a primitive root, and you're done. Okay, now maybe you're catching on. I'm putting a few of these theorems kind of slowly. Maybe you'd like to propose something in general about what we can say about squares, mod p, and their order. You want to tell me anything at all about the order of mod p of the number x squared versus the order mod p of x? Who's starting to get a feel for what this order is all about? Now, I've done some cases. I looked at the case where x was a primitive root. If x is a primitive root, then this right-hand side was p minus 1, and the left-hand side turned out to be p minus 1 over 2. Got a proposal? Make a conjecture? Well, here's where you might go with this. You might think that it's just half, that this order is somehow, since you've already squared the x, when you want to see what power you have to raise it to, you'd think you just kind of divide by 2, and that should work. And it kind of does, except for the fact that this doesn't even really make sense in some easy examples. I mean, let's go back to the case of working mod 7 again. For each of these different congruence classes mod x, I can look at the squares of those numbers. 1 squared is 1, 2 squared is 4, 9, 16, oh sorry, I should have said 2, because I'm working mod 7. 4 squared is 16, which is also congruent to 2. 25 is congruent to 4, mod 7, and 36 is congruent to 1. So this is a theorem about asking for the order of 1, 2, or 4, and how the orders of 1 or 2 or 4 compare to the orders of these other numbers. Well, sure enough, when I squared the 3, I got a number whose, oh, here, I forgot to put in this next line. So what is the order of x squared? The order of x squared is 1. The order of 4 we decided was 3. The order of 2 we decided was also 3. So in 2 cases, you kind of get a win. When you squared the 3, you got 2. The order of 3 was 6. The order of its square was only half as big. Same thing here. This number is the square of that number. So the order of this number turned out to be only half the order of that number. And it worked in this case too. But it doesn't work so well in that case or that case, or that case for that matter, simply because your order is an odd number, and it doesn't make any sense to take an odd number and cut it in half and expect that to be somebody else's order. So let me say it this way. It's this if the order mod p of x is even, and otherwise it's the same. Just to recap here, we actually ran into this situation where I was looking at orders mod 7. I looked at a few powers of 2, and I realized when I would come back to something congruent to 1. When it came time for 4, I realized, hey, wait, 4 is the square of 2, and I had already kind of mentally gone through all the powers of 2, so that included going through the powers of 4, but the process didn't end any faster for the 4 than it did for the 2, precisely because when I ran through the powers of 2, I didn't come back to a power, something congruent to 1, until I had raised the 2 to an odd exponent. So let's see if I can take that one example and give you a proof that illustrates the same concepts more generally. So let's break this into two cases. So suppose first that the order mod p of x is some even number, I'll call it 2 times n, for some integer n. So of course, exactly what that means is that x to this exponent is congruent to 1 modulo p, and if you use any lower exponent, x to the k, that's not congruent to 1 modulo p, if k is a positive number that's less than 2n. Positive number, less than 2n. Okay, the order is the smallest positive exponent that takes you back to a 1. All right, so in this case, when the order is even, this is the setting. There's some integer n that makes this equation true, and all the smaller integers, you don't get 1. Alrighty, well then we're supposed to start looking at x squared and raising that to various powers. So, can I think of an exponent that I can put on x squared to get something that's congruent to 1 mod p? Of course. Just raise that to the nth power. And now you know that this is congruent to 1 mod p. So what that tells you is among all of the exponents that you can put on this base, one of them that will work is to use the number n. So when if I ask you to look for the smallest one, the smallest exponent that would work with the base of x squared, that's going to have to be less than or equal to n. Actually, using that the Bézout lemma and so on, whenever I get a statement like this, I know that the order would actually have to divide the n, but I don't need that right this moment. All right, so the order is less than or equal to n. Now, can you find a smaller exponent that would work? Well, if indeed there is an exponent L that's, well, let's just have L be this order, then that means x squared raised to the L power is congruent to 1 modulo p, but that's x raised to an exponent, to L. And according to this statement over here, when you raise x to any exponent, you will not get 1 if that exponent is less than 2n. So based on this result, that means that this exponent here cannot be less than 2n. It has to be at least 2n. That means that L is at least equal to n. So now I know that the order mod p of x squared is greater than or equal to n. And when you compare these two things together, that says that L is obviously equal to n. In other words, L is this order, and it is exactly equal to this n, which is half of the order of mod p of x. Now, I'll pause here because I still have to do the other half, but let me just say that more generally, exactly this argument works when you replace this 2 here with any other exponent. If you're going to be looking at, if you take a number x and you raise it to a power which is a divisor of p minus 1, then the order of the new number that you've just created will be the order of the old number x that you had divided by that exponent. So going back to this case over here, if you take any of these 4 integers, you can see that their order is a multiple of 3. Well, then you take any of these 4 congruence classes and cube it. X cubed, 2 cubed will have an order of 3 divided by 3. 3 cubed will have an order of 6 divided by 3. 5 cubed will have an order of 6 divided by 3. So once you can get elements of a high order, you can get elements of lower orders by simply taking powers. And once we find primitive roots, that'll actually give an affirmative answer to the question that Yiglit was asking earlier. If you can just get a primitive root, then actually you'll have elements of every possible order, all the possible orders that are allowed by the previous theorems. To finish this theorem, though, the one I'm working on, let's go and consider the case of what happens when you have an element of odd order. So now suppose that the order mod p of x is equal to 2n plus 1, some odd number. And now let's think about what the order of x squared is. I already know that if I take x squared and I raise it to exactly this exponent, then my laws of exponents allow me to rewrite things in a different way, which will now be obviously congruent to 1 squared, which is 1 mod p. So as in all of these calculations, I've already done like phase 1 of my work. I have at least identified an exponent that I can put on this base to give me a 1. But now the question is, can you find a smaller one? Well, it's the same deal. If you know that if you have any other exponent that you can use on x squared to get a 1, if that's congruent to 1 modulo p, then I'm going to show you that actually this L cannot be any smaller than 2n plus 1. In fact, that would imply that, well, x to the 2L is congruent to 1. And now I've got 2 different exponents that I can put on x itself to give me a 1. So as in all of the previous times I've done this, when you have 2 exponents on the same base x that both give you a 1, then their x to their GCD of 2L and 2n plus 1, that's again going to be congruent to 1. Now here's the thing, 2n plus 1 is obviously it's an odd number. It's not divisible by 2 at all. So when you look for the greatest common divisor of 2L and 2n plus 1, it doesn't have any factors of 2 in it. You can't have any 2's dividing this factor, so you won't have any dividing the GCD either. So let's write that out. So the GCD of 2L and 2n plus 1 is equal to the GCD of just L and 2n plus 1. Okay, so now I know that x to the GCD of L and 2n plus 1, that's also congruent to 1 modulo p. But if the order of x modulo p is exactly 2n plus 1, then this number, which would be a divisor of 2n plus 1, it's going to have to actually be 2n plus 1. This GCD is always less than or equal to 2n plus 1. We've had this pair of inequalities before. But on the other hand, such an exponent has to be greater than or equal to 2n plus 1 by the definition of order. So my conclusion is the GCD is exactly equal to 2n plus 1. And when the GCD is that number, in particular, that means that 2n plus 1 divides L. So now I'm in trouble. Not in trouble, but I've just discovered that if you went for looking for any other exponent to put on the x squared to get something congruent to 1, all of those other exponents have to be multiples of the one that you found already. So the minimum value of L, the smallest possible exponent that you can put on the x squared, is in fact exactly 2n plus 1, which was the order mod p of x in the first place. So that was the other half of this theorem. When you look at something of odd order, then taking its square doesn't actually reduce the order at all. You have exactly the same order for x squared as you do for x. Okay, I've used up my hour, so let me just summarize this by saying I'm actually introducing you guys to a little bit more group theory. This is going to operate behind the scenes. I'm not going to write it down. But what you're really looking at is you're going to have, by looking at these powers of things, you're moving around inside a cyclic group. If you start with a primitive root, then every time you multiply by a primitive root, you'll be hopping around to a different element of z mod p cross. And this business of
So
taking...
it's a generator?
Yeah, it's going to be a generator. Primitive root in that language would be called a generator, exactly. And so all I'm discussing here is stuff like what happens if you decide to take 2 hops at once. Well, the answer then is that it only takes you half as long to hop around. If it originally took you 12 steps, 12 hops to come back to where you started, then if you go by double steps, you'll obviously only have to take 6 steps to come back where you started. If, on the other hand, it originally took you 13 iterations to come back where you started, then if you take steps that are twice as big, well, it's still going to take you 13 steps to come back. 6.5 steps isn't really a number of steps. So I didn't write that down. That's group theory language, and it's a little outside the realm of our course, but it does give you the spirit of what we're doing with all of these powers.
Can you show the very end of the proof we just wrote? Thank you.
Yep. So none of the other exponents that work can ever be smaller than 2n plus 1. They're actually multiples of 2n plus 1. All right, guys. I am going to put the exam up tomorrow at, I guess I'll put it up at 2 o'clock when our class is supposed to start. So on Thursday at 2, the exam will go up. I'll put a link to it on the course webpage. I'll put a link to it on Canvas. If I think of it, I'll try to send you guys an email actually to tell you that it's up. And then it'll be due at this time on Friday. Get it done by 3 o'clock on Friday. Either turn it in on Canvas the same way you do the homework, or just send it to me in an email. That'll work as well. Okay, and if you have any questions in the process, if you think that there's a typo or something, send me an email. I'll keep checking my email. If I discover that there is a typo, I'll send you guys an email back just to let you know. Okay, I'll make it doable. It'll be challenging, but I think you'll be able to do it.
I have a question.
Yes, certainly. Go ahead, Chica.
Is there gonna be like a bump with this stuff on it, or is this gonna be part
This
of the
stuff?
test? Yeah.
No. This is off. This is not part of the test.
Oh, okay.
Test
Also,
will
I have
only go.
another question about ordinance. What about the order of x to the n?
Yes, so I'm just doing squares here. Well, here's the general theorem. This will be a little preview. The general theorem is that when you take an element whose order you know, and you decide to raise it to a power, then you will, in general, reduce the order by a certain factor. You'll divide this order by a certain factor, and exactly what you're dividing it by is the GCD of the exponent that you're using and the order of the number that you started with. So this is just kind of a dry run to get you used to thinking about this. So you asked a great question that shows that you're starting to grasp what the idea of the order is. But I'll give you the theorem. I guess it'll be next Monday when we get around to it.
Also, this is probably not like part of the primitive roots, but what about when you have an order of a polynomial that isn't like doesn't have real roots.
I don't know what you mean by polynomial. You're talking about just, you're thinking of that as a polynomial?
Yeah.
Oh, that's, it's not just a question about real roots or not. Your question should be, how would you, what if you decided to manipulate a number x in z mod p by doing anything to it other than simply raising it to a power? Then now what can you tell me about how the order changes? And the answer is nobody has a clue. Even just a very simple question of, if I already know the order of x, can you tell me the order of x plus 1? And the answer is no, I can't tell you that. Nobody knows. There's really no pattern there.
Oh, okay. Thank you.
Yep. All righty, guys. I got an office hour now if you want to ask me questions. Otherwise, send me last minute emails if you get stuck on something. And if not that, then I'll be giving you an exam tomorrow. And good luck if I don't see you before then.